same process. We also wanted to modernize the power supply. It had some issues, I'm going to talk about it later. And also we wanted to expand the features by adding, by enabling it to communicate with PC through different modules like LabJack UE9 and PLC module. Also, some of the components were discontinued and it was hard to find them, so we wanted to use newer components. The unit was originally designed in 1996 by Professor Niyosha, and it has been used in courses CSC 453, PRG 553, and ATA 653 so far. This is how it looks. It's been designed by wire wrapping technique, which is not in, which is kind of like old technique to make boards, and also the components were obsolete. In 2012, a group of students modified the circuit by creating a PCB for it. They managed to create 4 pieces of PCB for it, which made it modular, and it was easier to test and troubleshoot the board because they added test points to it. But it was not enough. So the very first problem with the design was the power supply. It worked at different AC and DC levels, and also it was not CSA approved. So what we did was to look for a new power supply and design a circuit for that works at 24 volt DC only, and it's CSA approved, and that makes Hattie very happy. The old board used to communicate with the PC through IoTech DAC 100, and previous group changed it to LabJack U3, which was a great step forward. But what we did was to modify the circuit so that it can communicate through LabJack UE9 and also PLC modules. LabJack UE9 has 14 analog inputs and 2 analog outputs, 12 bits resolution, which is more than enough for the designs you need to use in the labs. And also it can be accessed through the internet, so you can access it remotely easily. So I would like, it is also capable of communicating to the PC through PLC interface compact logic 1769 module. It is a fast, high resolution analog module, and it has a fast dynamic response time, and it can be connected to the unit through DB15 connector. I would like to ask David to give us some more information about the dynamic response.
Good afternoon. We made the chamber heating power from 23 to 42, and we choose a much strong fan, so the chamber can heating up faster and the cooling down very faster, so we can save time. This is our circuit diagram for LabJack. We have 2 power supply, one is 24, one is 5, and we have 4 components. PWM, IC, and the 4M25 isolator, and the TIP 122 balancing transistor. And we also have a 5 regulator for the PLC. This is a circuit for LabJack, but we must working with PLC and the LabJack how to make a circuit can work for both. We have a solution. You can see. When we disconnect the LabJack and plug in the PLC, you will get a 3-wire jumper in the DB15 connector, so automatically changing the circuit for work with PLC. And disconnected the 5 voltage from the UE9. We didn't duplicate any component, and very convenient for this circuit to work. And now it's a little bit detail about which component how to work, and they are parameters. You see, we have a very small, tiny PWM. It's hard to solidate it, but we make it. And this PWM get input from PLC and UE9 and output a rectangular wave. The duty cycle can be changed from 0 to 100 and the frequency is 255. The next one is isolator. For N25, we using this one to separate the circuit with 24 voltage and the 5 voltage to protect the left jack. And by choosing appropriate parameter, we make the 2N25 working in a saturated state. So the VCE is very small and close to 0, so it will work perfectly. So now we're talking about the Darlington amplifier. It's a bigger current, maybe close to 2 amp. So easy to heating. So we make it work in saturator, and we add a heat sink to help it dissipate the heat. We found our circuit is good, but not when the maximum power supply is not heat up, it will live a long period. And we also modify the airflow center. We choose this circuit from professor, and we build this circuit. We made a good thing. So the older one is minus 12 and positive 12 to power supply. Now we just have one power supply is 5, and the output range before is negative 900 millivolt to 1.8 volt. Now we get from 0 to 3.8. It with high accuracy and easy to interface to PLC and laptop. We also connected the chamber to the PLC compact logic. We configure the analog module, and we can using the compact logic to control the chamber, the fan speed, the heat up. Even we can do PID tuning, and this is just an example.
And also, the unit is capable of communicating to the laptop through visualbasic.net. As you can see, the program can run in automatic and manual mode. This is the automatic mode, which you set the set point to a specific value, and the system adjusts itself to reach that set point. Also, there is the manual mode where you can control the outputs manually.
So hi, I'm Daniel. I'm going to talking about the PCB design. So for the first board, they use the one board with no wire wrapping, and for the first modification, they use for PCB design. However, for our modification, we only use one PCB design, and that less footprint and less time spent on the instruction, less component, and cheaper to manufacture. So here is more detail about what I'm talking about. As you can see, here we only the size we almost just use the 1/3 of the previous one. So here is more information about the number of components. For our multiplication, we only have 37 components, almost half of the previous one. Less component, less manufacture, less cost. The Paddy will help with that. So we use PICE to design the PCB circuit. First, we design a schematic in the paste logic, and then export them to the paste layout. The challenging we have to design a circuit. First, we need to create our own component because there is a lot of components that exist in the library. So here is the barrier connector and the heat sink. For the barrier connector, because the manufacturer cannot make a square holes, so we need to use the multiple circle holes to instead of that. We also need to consider the components, the position, and the space. For example, as you can see here is the test point. We designed test point size of the bulb, so it can make us easy to access the data. And another challenge is choosing the correctly trace and the hole size. As you can see here, we designed a big trace because there is a big current to go through there. If we use the small trace, it might melt on the trace. The lesson I learned from using the Pi solver, it is because I designed a circuit first in the Pace Logic A is for to layout. But after that, we are updating the circuit without updating the Pace Logic. So it will cause our hard to troubleshooting the circuit.
So this is the summary of what we did. This is the old ancient board, which is going to be replaced by our beautiful, wonderful modification design, hopefully this summer. And we wanted to thank Professor Rogers for being patient enough to answer every single question we had 24/7, and also Mr. Hadi Maizu for funding and supporting our project. Let's take a look at design. So it's currently running in manual mode. We can change the the light bulb intensity. This is the 100%, which means maximum. Also back to 0. And also the fan can be controlled. Now look at the bulb temperature shown here in this text box. As I increase the bulb intensity, we expect it to go higher, which is happening. Now, if I increase the fan speed, it has to go down. Yeah, thank you.
So this one is the L4.
So it varies between 0 and 100%. So right now it is, it's at maximum. And as we slow down the fan, we see the airflow to decrease. Now we go to automatic mode and set the set point to temperature higher than the bulb temperature.
So light bulb will turn on, the temperature will increase to get the set point.
As you can see, it is dimming to adjust. That's it. So you have any questions?
What are some of the other challenges that you experienced while doing the project? Not related to pads, I have lots of challenges about pads. But what's
So the power supply we're using here is running at 24 volts and 4 amps, which is a high current. For 24 volts, that's a really high current, and it's hard to find a power supply running at that current. So it was one of the challenges we had.
Another challenge is troubleshooting. We built this PCB, but if this PCB doesn't work, I must trace every line and every connect have to find the problem. Sometimes they also hard work.
You had some other problems with the optical isolator. Can you say something about that?
Yeah. So when we use the 425, the 6 pin, if we use the 6 pin to plug in the socket, the circuit doesn't work. However, if we remove the pin 6 and plug in there, it will work. But the pin 6 doesn't connect to anything.
Yeah, it is supposed to be a not connected pin, but surprisingly, when it was connected to the board, nothing works. So what we did was to cut pin 6 here. If you come closer, you can see that pin 6 is missing. So that was the problem. Optimize later, 425.
How did you make these numbers
So, here reading the values on one of the input ports of the lab between 0 and 100. Should we show here as percentage? Because that's what they would want.
very good? So what's the next step in this project, since you're doing it for Seneca?
Okay, hopefully this is going to be deployed in B1028. It's going to be, unfortunately we cannot print silk screen PCB here, so we have to ask an outside company to build the PCB for us. And once that is done, we are going to deploy it in B1028 in summer.
Good. Any other questions?
Yes.
Stromal.
How long did it take you to work on your project?
Forever.
So every afternoon after classes, weekends until 6, 7.
They're getting emails from them all weekend long, late into the night, 10 o'clock at night, 11.
Hard working.
And also my time.
Which doesn't cost anything.
What's the other future things you see for that? You talk about deploying in B1028.
Yeah.
We made a BDM and we will maybe we recommend to make some for the curriculum to using our new channel because the older one not enough and the dynamic responsiveness is slow.
Also, we need to make a bill of material on DigiKey because that's how Hani likes to order stuff.
So all the things you learned at Seneca College came to bear on this project. Well, really well done. Thank you very much. The next presentation will be at 2 minutes.